Welcome again to Let's Talk Advanced Chemistry, Chemistry 2 with Pastor Dan. We're going to look at gas laws. And again, remember, if you're having issues with these, you need help, first of all, you can email me at ltswpd@gmail.com. Also, I do have these in my Chem 1 video playlist. So go back to day 135 to 145 and list all the gas laws and all the practices and all the examples and all that kind of good stuff. So let's get started with the gas laws. When we talked about gas laws, remember we talked about the three. When we start with that is Charles' law, Boyle's law, and Gay-Lussac's law. Charles' law says that pressure remain constant. So P1 over T1 is equal to P2 over V2. Boyle's law never boils, so temperature remains.
Actually, that's wrong. It's V1 over T1 is V2 over T2.
It's constant, so it's P1 V1 equals P2 V2, and Gay-Lussac's law volume remains constant, so I think I got that wrong. V1 over T. I'll show them to you. Here we go. There we go. V1 over T1 for Charles' law. V2 over T2. P1 V1 over T1. P1 V1 equal P2 V2 for Boyle's law. And Gay-Lussac's law, P1 over T1, P2 over V2. Now we put those all together, we get a combined gas law. Just makes it easier to use. Even if we're using one of the gas laws, the value that's opposite, we just cross out and you have the gas laws present. The other gas laws we worked with is Graham's law. Graham's law deals with the rate of diffusion, and it has the inverse rate of square root of the densities or the inverse square root of molecular weights. Dalton's law says that the total pressure is equal to the sum of the partial pressures. And the ideal gas law identifies that we have various relationships for one gas only, and can do it in terms of moles, mass, or density. All right, so those are our gas laws. So let's get started with the first one. Let's do combined gas law. When we do this, we're going to do P1 V1 is equal over T1 is equal to P2 V2 over T2. Determine the volume of gas at 18.9 degrees Celsius and 1.098 atmospheres. If at STP, the volume is 70.22 liters. Now, remember I told you before, we're looking for that preposition, that if. So we get an if here, this is the divider, so this is the first half, this is the second half. And remember, we do combine gas laws when we have two sets of conditions, two pressures, two volumes, two temperatures. So our starting pressure is 1.098 atmospheres, and we don't know the volume because it determined the volume in the first half, and the temperature is 18.9 degrees Celsius, but we don't like Celsius because it's got 0 in it, so therefore we're going to convert to Kelvin, add 273. So other values are STP, so we have 1 atmosphere, 70.22 is listed there, and standard temperature is 273 degrees Celsius. All right, so we take our second half of the equation, P2 V2 over T2, so we have V1. That means T1 has got to go up, it was down. That means P1's got to go down, it was up. Put our values in. When we cross out our units, atmospheres cross out, kelvins cross out, we're going to get 68.38 liters. We have infinite significance, 4 sig figs, infinite 4 sig figs. So 4 sig figs is my answer. That is my answer right there. All right, let's look at another value here. Now, this is the one I wanted to show you. This is a little bit different. Determine the density. Now, there's no density in there, so how do we do that? Well, let's start with the given information we have. Okay, we have 108 because it's before the if. 0.2, we don't know the volume because it's the density we don't know. Temperature, I convert 90.44 into Kelvin already, so we get 363.44 Kelvin. After, in kilopascals, standard is 101.3 kilopascals. I'm going to leave this blank just a second, and 273 Kelvin is standard again. Now, I have a density here, but I don't want to put that in there because that's not density. That's volume. So what volume do we have here? Well, we have 1.055 grams. I don't want the mass. In how many liters? 1 liter. So that's my volume. That 1 liter I have from the density. All right, so do the same thing we did. Can solve for V1. Put our values in. So this should be kilopascals here. I apologize. Oh, I did get rid of that. Get rid of that there. All right. So we have kilopascals, cross out, Kelvin, cross out. When we multiply that through, we get 4 sig figs, 5 sig figs, infinite, 4 sig figs. So to 4 sig figs, we get 1.246 liters. Now that's not my answer. That's how much the volume changed. Remember, density is defined as D equals M over V. My mass is still 1.055 grams, but the volume is now changed. Instead of being 1 liter, it's 1.246 liters. That's going to change the density, okay? Because although the mass didn't change, the volume did. So my new volume, 4 sig figs, I'm going to have 4 sig figs. I get 0.8467 grams per liter. So that's how we do a density problem with combined gas law. All right, let's look at the next gas law, which is Graham's law. Graham's law deals with the rate of diffusion. Now, remember, we're looking here for that comparison. The first rate of diffusion versus the second rate of reaction, and that's going to give us a number. The density of the first one is 1.124 grams per liter. Density of the second gas is 0.8766 grams per liter. If the rate is greater than 1, it's faster. If the rate is less than 1, it's slower. We put the values in, and we get 0.7799. But remember, it's a square root of both sides. So square root gives me 0.8831, which is slower. So we're saying gas 1 is 0.8831 times lower because 4 sig figs, and that's my answer right there. All right, let's take a look at the opposite problem. We're going to do molecular weights now. Remember, the atomic mass of fluorine is 19, oxygen is 16, but they're both diatomics, so we have to double them, F2O2, and we're going to do oxygen on top. So oxygen, 32 grams per mole, units for molecular weight. 19 times 2, 38 grams per mole. Square root of that, I'm going to get 0.9177 times slower, less than 1. I use only 4 sig figs. There's infinite sig figs, so I have to pick a number. For my teaching, I always say do 4 sig figs. When in doubt, do 4 sig figs. All right, so we're going to say fluorine is 0.9177 times slower than oxygen. All right, Dalton's law. All right, so in this case, we're going to do a little bit of a difference here. For this problem, we're going to say, I want to find what percentage that volume of that first gas is compared to the whole volume. And then I multiply that percentage by the total pressure to get the partial pressure. So in this case, we're doing oxygen. So we'll take the volume of oxygen divided by total volume of oxygen times the total pressure. So put our values in. Well, we say 15.67 liters is oxygen. That makes sense. Where did I get the 30.1000? Well, I'm going to add these two together. If I add 15.678 liters and 14.322 liters, I get 30.00, and the total pressure, I've got 5 sig figs, 4 sig figs, least number 4 sig figs. I get 412.0 torr when I do that because my liters will cross out. We do the nitrogen, same thing, except it's going to be 14.322 liters divided by 30.000 liters divided by 788.4 torr. Now, those are my two answers because I asked for them both. If I ask for just one, that's all I have to do. There's a check on it to see if you did it right. If you add those together, if you take 712.0 torr and 376.4 torr, add them together, you should get 788.4 torr, which it is, and that is correct. All right, the other way we can do this is collecting over water. Now, to do collecting over water, we have to have the water vapor chart, remember, and we go back here a second. The temperature is 16 degrees Celsius, so if you look at 16 degrees Celsius, it's 13.6 millimeters of mercury. So we take our Dalton's law equation, we're only collecting 2 gases, water vapor and chlorine gas. Total pressure. Total pressure is the barometric pressure. Remember, the pressure inside is always equal when you're pushing out. So 733.9 is equal to pressure chlorine. And that water vapor we got, 13.6. Simple math, all we're going to do is subtract and get 720.3 millimeters of mercury. I'm going fast. This is all review. Hopefully not too bad. All right. Lastly, ideal gas laws. Now remember, this is going to look an awful lot like combined. But combined, there's two sets of conditions. In ideal, there's only one temperature, one pressure, one volume. We've got three gas laws. We use the first one, dealing with moles, or asked to find moles. Second one, mass. The third, density. Well, in this one, we see there are moles, so we're going to use that equation. Now, I've got two possibilities for R, 0.0821 liters atmospheres per mole Kelvin, or 8.31 liter kilopascals per mole Kelvin. And I'm going to use atmospheres. I just like that one better. So we're going to solve for nRT. That's the opposite volume. Volume comes down, put our values in, cross our units out, left with atmospheres. We get 3.288, 4 sig figs, infinite, 5 sig figs, 4, least numbers 4. So we get 3.288 atmospheres. All right, try this one on your own. Pause the video. Try this one on the own. It's pretty straightforward algebra. Okay, here we go. There's our answer, 61.77 grams. All right, that's it. We're done. Take care. God bless. Hopefully not too bad. Bye.